guys, welcome to Module 2 which covers vectors and geometry of space. So in this lesson, I'll talk about the vectors in the plane. And at the end of this lesson, you should be able to, number 1, write the component form of a vector. Second, perform vector operations and interpret the results geometrically. And third, write the vector as a linear combination of standard unit vectors. Many quantities in geometry and physics, such as area, volume, temperature, mass, and time, can be characterized by a single real number that is scaled to appropriate units of measure. So these are called scalar quantities, and the real number associated with each is called a scalar. Other quantities such as force, velocity, and acceleration involve both magnitude and direction and cannot be characterized completely by a single real number. The set of all directed line segments that are equivalent to a given directed line segment P to Q is a vector in the plane, and this is denoted by this notation. So this is read as vector V, with which is equal to a directed line segment from P to Q, where P is the initial point and Q is the terminal point. In typeset material form, vectors are usually denoted by lowercase bold-faced letters such as U, B, and W. And when written by hand, however, vectors are often denoted by letters with arrows above them such as U, B, and W. Okay, so as an example, suppose you're given a vector V, which is represented by the directed line segment from 0.00 to 32, and let U be represented by the directed line segment from 0.12 to 0.44. So we have to show that B and U are equivalent. So to show that these two vectors are equivalent, now we have to show this geometrically, that they have the same direction. So we first plot the initial and the terminal point of each vector. So for vector B, the initial is at the origin 0, 0, and the terminal point is at 3, 2, which is 3 units away from Y and 2 units away from the x-axis. So connecting these 2 points, so we now have the directed line segment from P to Q, or also same as the vector B. Okay, for vector U, the initial point is at 1, 2, which is 1 unit away from Y and 2 units away from X. And let this point be as R. Then the terminal point is at 4, 4, which is 4 units away from Y and 4 units away from X. And let this point be as S. So connecting these 2 points, so we now have the directed line segment from R to S, which is our vector U. So geometrically, because the two vectors are of the same direction, the next thing that we have to show is we have to show that they have the same length. Okay, for vector, you recall in analytic geometry that to find the length or the distance between 2 points, so we make use of the distance formula, which is equal to the square root of x sub 2 minus x sub 1 quantity squared plus y sub 2 minus y sub 1 quantity squared. So your x sub 2 here for vector u is this is your x sub 2, this is your x sub 1, y2, y1. So for x2 minus x1, you have 4 minus 1 quantity squared plus y2 minus y1 is 4 minus 2 quantity squared. But 4 minus 1 is 3, so 3 squared is 9. 4 minus 2 is 2, 2 squared is 4. So 9 plus 4 is 13. So therefore, the length of this vector u is square root of 13 units. Okay, for vector b, we use the same formula. This is equal to the square root of the x sub 2 minus x sub 1, which is 3 minus 0 quantity squared, plus y2 minus y1, or 2 minus 0 quantity squared. But 3 minus 0 is 3, and 3 squared is 9. 2 minus 0 is 2, and 2 squared is 4. And 9 plus 4 is 13, so we have square root of 13 units as the length of vector b, same as the length of vector u. Okay, after showing that the two vectors are of the same length, now we have to show that they have the same direction using the slope. So recall that to find the slope, the formula is y2 minus y1 over x2 minus x1, where x1, y1 is the uh, x and y coordinate of the initial point P, and x2, y2 are the coordinates of the terminal point Q. So from the formula, the distance is the slope rather is 2 minus 0 all over 3 minus 0, which is 2 over 3. Then the slope of the second vector with initial point at R, terminal point at S, is equal to 4 minus 2 all over 4 minus 1, which is equal also to 2 over 3. So as you can see, because their slopes are equal, so we can conclude that these two vectors are of the same direction. And therefore, we can therefore conclude that since these two vectors P to Q and R to S have the same length and direction, so we can conclude that they are equivalent. That is, vectors B and U are said to be equivalent vectors. The directed line segment whose initial point is at the origin is often the most convenient representative of a set of equivalent directed line segments, such as shown in this figure. So this representation of vector B is said to be in standard position. A directed line segment whose initial point is at the origin can be uniquely represented by the coordinates of its terminal point Q with coordinates b1, b2. So in the definition, note that the difference in the notation between the component form of a vector B with components b1, b2 and the point with coordinates b1, b2. So by definition, if B is a vector in the plane whose initial point is at the origin and whose terminal point is at b1, b2, then the component form of vector B is denoted by this equation. Vector B is a vector with components b1, b2. So take note that we use the less than and the greater than symbol to denote the components of this vector B. The coordinates of vector b1 and b2, these are called the components of vector B. So if both the initial point and the terminal point lie at the origin, then we can say that B is a zero vector, and this is denoted by this equation. 0 is a zero vector with components both equal to 0. So this definition implies that the two vectors u and b, where u is a vector with components u1, u2, and b is a vector with components b1, b2, are said to be equal if and only if their corresponding components are equal. That is, u sub 1 equals b sub 1 and u sub 2 equals b sub 2. So the procedure listed below can be used to convert the directed line segments to component form or vice versa. So if the initial point and the terminal point of the given vector are given, then the component form of the vector B represented by this vector from P to Q is defined using this equation. So the vector with components b1, b2 is equal to the difference between the uh, x coordinates of Q and P. So you have Q1 minus P1 and the Y coordinates of Q and P, which is Q2 minus P sub 2. So moreover, to find the distance of this vector B, we make use of this formula. So this is called the length or magnitude of vector B, and this is equal to the square root of the sum of the square of the difference of first to first components. So you have q1 minus p1 quantity squared plus the difference between their y coordinates. So you have q2 minus p2 quantity raised to the second power, or this is simply the same as the square root of the first component of vector b plus the square of the second component of vector b. And number 2, if B is a vector with components B1, B2, then this vector B can be represented by the directed line segment in standard position from the origin with coordinates 0, 0 to point Q with coordinates B1, B2. So the length of this vector B is called the norm of vector B. And if the length of this vector B is equal to 1, then we can say that B is a unit vector. Moreover, the length of the vector B is 0 if and only if B is the 0 vector. So in summary, if B is a vector in the plane with initial point at the origin and terminal point at vector B, then the component form of vector B is denoted by this notation B1, B2, where B1, B2 are called the components of vector B. So if both the initial point and the terminal point lie at the origin, then we can say that the vector B is called the zero vector, and this is denoted by this notation. Also, the two vectors u and b are said to be equal if and only if their corresponding components are equal. That is, u1 equals b1 and u2 equals b sub 2. Okay, suppose given the initial point P and the terminal point Q of the vector from P to Q. So the component form of this vector from P to Q is obtained by subtracting their corresponding coordinates. So you have Q1 minus P1, comma, and then Q2 minus P2. So these are the components of the vector with initial point at P, terminal point at Q. So to find the length of this vector from P to Q, we make use of the distance formula, which is equal to the square root of the sum of the square of the difference of their, or the square of the first and the second component. So you have the square root of the square of the first component, q1 minus p1, plus the square of the second component, q2 minus p2. But this is also the same as the square root of the square of the first component, b1. So you have b sub 1 squared plus the square of the second component. So you have b sub 2 squared.